so it puts it on 0 for all the bytes. So that's why you lose all the bit 1 in the key. So the last one is 7E. That's a good guess because we put in 7F. So this is basic the principle of breaking a DES key. Anyone got any questions on this part?
You always add that parity bit back in to 1, or is that?
No, because if you just put them in as bytes, like a key, it's also not a parity bit, right? If you just put in hex data, it's just lost. The parity bit generally is not used anymore in DES. So.
How fast is this processor
running the smart card, you mean? It's running at 4 megahertz and 3 clock cycles per instruction. Okay. Then I'll move over to countermeasures. So what do you want to do with your countermeasures to prevent something like this? Well, there are two things. You want to decrease the leakage. Now, like I said, I was assuming that we have no control over the hardware, so we have to do something else to decrease leakage. One thing is to balance values. Like I said, we use the model of a Hamming weight. So if you make sure that all your Hamming weights in your processing are always equal, maybe you'll leak less. One way is also to limit the number of operations per key, so the limit on the transactions, but maybe also a protocol change. The other thing is to increase noise. Now, again, we just don't have the capability to add a hardware noise generator to our embedded system if it's in the CPU. But we can change timing. All the correlation depends on that everything is happening at the same time, at the same column in our measurement. I mean, it doesn't have to be at the measurement time, but at least we need to be able to shift it back into the same column for it to work in a correlation. So if we can make the timing very noisy, that would help. There are basically two concepts that you have in doing this in passive side channel. One is hiding. Hiding is a concept that you try to make it difficult for the attacker to know when a certain value is being processed. So you don't really change the fact that you have to process this value in your program, but you do make it difficult for the attacker to find when. And the other one is called masking or blinding. And with this type of countermeasure, you're trying to change the values that you are processing in your program without the attacker being able to know what you're processing. Basically, what you do is you mix in a random value in your algorithm and use that throughout, somehow masking the real operations that you're doing. At the end, being able to reverse the effect and extract your real output that you're looking for. So basically, you can see it like this. You have an algorithmic value, like, okay, I'm doing a DES with this key, then I have to do this kind of operation. By changing the algorithm by using a random value, for instance, to mask it in, you change the value that the actual XOR instruction is processing. So the power consumption is also related to that new process value, making it difficult for an attacker to know. And then you hide it. You try to make it very difficult for an attacker to know when this value is being processed. Going a little step back, actually, you can already do a lot by just changing your protocol. I've taken here a picture from a paper by Paul Kocher, and it's about using a key in a way that it's actually being used only once. So you start out with a key, and in this case you do have to have a server that knows at what stage you are in your transaction. So there needs to be some kind of synchronous system so that both sides know at what stage in the transaction they are to know how to process and generate a new key. But if your SHA operation is leaking, then you'll never leak more than 2 SHA operations. And if that's only a couple of bits per SHA operation that you're leaking, then you'll never leak the complete key. So this is a way to prevent leakage. Well, now I just have more or less a random bag of examples. Let me check the time because I also want to give a demo. So I'll go over this a little bit quickly. Well, first of all, time dependency. You do want to remove time dependency. That's going back again to the timing attacks. And that's not only the instruction timing, but also the fact that you do conditional branches on things that are determined by key material. A very simple one is inserting random knobs. You know, if you just start inserting random knobs for an attacker, as long as he can't distinguish those knobs from other instructions, or can recognize the parts he's interested in, you can confuse an attacker and make it more difficult. You'll definitely need to take more measurements to get the same amount of information out of each position in time. Another one is changing order. So if you've got multiple operations that need to be done that don't depend on each other, you can move them around. Like S-boxes, generally everyone goes through S-box 0, 1, 2, 3, 4, 5, 6, 7. But it isn't necessary. You can calculate them in any order. If you do that, you reduce the chance for an attacker because he has to take many more traces to get the same amount of correlation for each S-box position. It goes something like, if you've got 8 S-boxes, your correlation, to get the same correlation, you need 8 times 8 more traces. So 64 times more traces. It goes by the square. So that's significant. So if you take 100,000 traces and you have to take 6.4 million, that's a significant difference. Because we do these measurements, and sometimes they take like 4 or 5 days for a measurement set, and only then you can start processing to find out that you did it wrong or something like that. So it can be quite an obstacle. Well, and then of course you can implement a masked version or blinding, and RSA that's particularly well known. Actually, in OpenSSL currently also has a blinded RSA. Against timing attacks. Okay, more demos. So we go back to the DES measurement on the OMAP board. And what I show is the effect of inserting some random information in there. So what we have here is a DES, and it's always operating with the same input data. So it's not changing or random input. So this is always the same input without any countermeasure. So if you scroll through these, you'll see that there's almost no difference. They line up nicely. So also here the sidechannel attack works really well. I didn't do it live because it takes a little more measurements, like 20,000, but it works. So now we have a version that inserts randoms, all places through the DES operation, and still with the same input data. So there's no difference. It's not any variation you see is not from the input data and not from the key. So you can already see in the measurement below that it's, I'm not sure how many is it taking? 100. Better not go through all the 100. So if you scroll through this, you already see that it will shift in time, it will shift in amplitude, purely from introducing some random knobs in this algorithm. And this will take significantly more measurements to break. Okay, another example is RSA. A very basic RSA implementation. So we move the probe. For some reason, the RSA is better visible on another part of the chip. I don't know why. Maybe it's also not when you do a DPA, but for the SPA that we now do, it's much better. So this is only taking one measurement, and well, let's see what we find. We do a little bit of low pass filtering on this one to make it more visible. Yay. Okay, so what do we see? Are you familiar with RSA implementations? Well, what you do in an RSA is an exponentiation. And for each bit in the exponent, you do a square operation. And if the bit is 1, you do an additional multiply. And what we see here is you see each peak downwards is the boundary between a square or a multiply. And then where the dark bit is, that's the multiply operation. So I don't have a pointer, but oh yeah, better just do it that way. That's easier.
This one.
So what we have here is a square, 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 multiply. So what does it mean? That means a 0 bit, a 0 bit, a 0 bit, a 1 bit, a 1 bit, a 1 bit, a 0 bit, a 1 bit. So that's the secret exponent of RSA that you see there. Now this is a well-known issue with RSA if you implement it very straightforward. So a simple countermeasure against this SPA, and I do want to say this is not the best countermeasure, is to do a so-called bit group-wise implementation. If you do a little mathematics, you can make it clear that you can do pre-compute a couple of multipliers, and then what you do is a square-square multiply with a pre-computed multiplier, but then for every bit group. And that means that it's a constant. You get square-square multiply, square-square multiply, irrespective if the bits of the exponent are 0, 0, 0, 1, 1, 0, or 1, 1. And because you can't see the difference between the multipliers, you don't visually see any difference anymore. So that's what we see here. Now it's all the same. Well, probably you didn't remember, but down here at the bottom, you see the result of the encryption. And it's the same answer as the previous one. So the algorithm didn't change, the input didn't change, and the result didn't change. But you do see that visually there's now no noticeable difference anymore. Now, that doesn't mean that this is secured against a timing attack. For a timing attack, this does nothing. So there are countermeasures for different reasons, and you probably should combine them to make a secure implementations. Let me quickly switch. Well, this is what I was explaining, so I won't go. This is off. Has the slide been this crooked all the time? I'm not sure if this... Oh well, sorry about that. This was the implementation that is simple, and this is the bit group, but I don't want to go too deep in this kind of mathematics. Another implementation in this measure is blinding. It's a kind of masking on RSA. The way you do that is, in this case, you change your message, your input message, by multiplying it with a random value, and then perform the RSA on that value.